So, hello to everyone in YouTube land. Hello to everyone in Zoom land. If you want to know, if you're in Zoom land, you can see the lovely picture of the lovely castle behind me. This is just one of the many castles we have in Belgium. So if you want to come and work with us in Leuven and see these beautiful castles, please come and do so. But let's go on to the main event of the day, which is Moti, who is, well, actually basically needs no introduction, but he's going to talk about the big bad adversary. So over to you, Moti.
Thank you very much, Nigel. So I'm sorry for not publishing a title and an abstract. I was a little bit busy, and but it's TBA, so it's still TBA, the bad adversary, dealing with Malice, not in the streets of New York or Minneapolis, but in private set intersection cardinality sum problem. And I will talk about the problem, motivation that will be based on the honest but curious solution. And then I will talk about how to move to deal with malicious adversary when you really care about efficiency. And then this will give us some design methodology and general way to talk about protocols. So essentially, this talk is based on two papers. The first one on deploying secure computing commercially, private intersection sum. It was supposed to be in EuroS security and privacy in March, but the conference was delayed, but it's available on ePrint. And the second one is two-sided malicious security for the same problem, which will appear in crypto. So, okay, so maliciously secure, or sometimes we, instead of saying maliciously secure, we just say malicious. We don't want private set intersection with of cardinality and sum. And let's start with looking at the problem and the motivation for the problem. So think about two players, Google and a merchant who's called Macy's. So they have list. They have list of, set of users. Let's say these are their names, and they want to compute the private set intersection. And they're engaged in a protocol. And at the end, since the common elements in the list are Bob and Eric, they both compute Bob and Eric. I think this is a very well-known problem. Everybody knows, almost everybody knows set intersection and private set intersection. It's been and is being in research for quite a while. It's a specialized protocols of secure computing, and it is an interesting problem, and this shows you an e-commerce setting between two e-commerce players, how they can use it.
Could you just a minute, Moti? We've still only got your title slide on the screen. Is that correct?
You want me to restart?
No, just go. Yeah, just get to. Yeah, it's okay. Just go through the slides. You see, are the slides not advancing your side? I've only seen that. We can only see the title slide.
1 second. Oh, something is wrong. So I'm sharing a window now. Do you see the title slide?
We don't see anything shared at the moment.
Interesting. I share the screen again.
No, nothing sharing.
1 second. I'm correcting it. 1 second.
Okay.
I'm sorry for that. Now it should be okay.
Wait a sec. It's starting. It's starting. Very slow. Very, very, very slow. Yeah. Okay. Now see if you can advance the slide. That's the title screen. Yeah. Now we're
Outline.
there. Yeah. Good. 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 Okay. Thank
So
you.
outline, let's talk about it. I will define the problem. The main problem of interest is private set intersection cardinality sum. I'll talk about motivation, efficient and design. I mentioned the two papers on which it is based. They are both going to appear. The ePrint number is here. The first one presents the problem and deals with the benign case, honest but curious. And the second one is the bulk of this talk about malicious. What do you do in the malicious case when they are mutually suspicious party and they want to follow the protocol? And you still want to run it as efficient as possible, and there's no free lunch. You have to work for it. Okay, and then I said what is the problem and why, and people are actually know what the problem is, but Nigel, do you see the intersection calculated?
Yes, I do. I see everything. It's perfect.
Yes. So you see that Bob and Eric are in the intersection. Eve is not in the intersection, so she is not calculated, and Dave is not, and so on. So this is it. It's a very well-known problem, and it's just here put in the context of two companies that want to compute something in common. And the public set intersection cardinality, what we want to calculate is essentially, since it's Bob and Eric, we want the two parties to just calculate the number 2, the size of the intersection, obviously. And and PSI, public set intersection augmented with sum, is the case that one of the parties have associated with it, with the element of the set, certain numbers, and you want to calculate the sum of the intersection element. So it's Bob and Eric, 10 plus 120. If I'm not mistaken, it's 130. So this is what you want to calculate. And these problems apparently, size and sum are interesting commercial entities that people want to calculate. Often the cardinality, but at some points also the sum, and this helped parties over the internet who are engaged in some e-commerce arrangement to understand whether the arrangement is working or not. Because there is some affinity program on behalf of Macy's that Google runs, and they want to show how effective it is. And on the other hand, there is, first of all, user privacy. You cannot, and commercial trade secrets that they don't want really to share the data. And that was the idea to produce, to use cryptographic protocols to this end. And of course, you want there is a need to do it efficiently, and let's start with the honest but curious case. So assume the two parties, they are still G and M as before. They will change name soon. And the first solution that comes, the first actual solution for this problem was based on commutative encryption. So you see on the first flow, G has a bunch of has its list G1 to Gn. So it encrypts it with its commutative encryption element and sends it to the other side to M. It's blue here, so M takes its commutative encryption key and applies to this set, and you get this F to the G to the GI, and also it takes its set F of M1 up to F of Mn, and the associated encryption here, and send it back to the other side. And notice that the doubly encrypted set is sent shuffled. So G sends a vector of elements, and he gets this vector of elements shuffled after F of M is applied to it, and the set of M. And then it picks up the red set F of M1 up to F of Mn and applies to it its encryptor, and it gets the doubly encrypted element of M. And because of commutativity, F of G is G of F. These two elements are encryptions of the elements, and then G can find the intersection size by finding matches between GF of GI and FG of MJ. If they equal, the original number was there. This is commutative encryption. Before we go, so in case M does not shuffle the set, in case it doesn't shuffle the case, G, because it remembers the positions of the original G1 to Gn, when it calculates the matching, it can actually calculate the set intersection. If it shuffles it, it loses the original value and only counts the number of matches. Of course, everything is proven. I'm not just saying it. And this is a way to get two birds with one stone, and it's always good for practice. If you can, with a little change in the protocol, get it to be multi-use, it's good. So assume we do the shuffle, so it only count matching, and it gets the intersection, the sum. And now to continue and get the cardinality, and now to continue and getting the sum, each element here that was in the matching has an associated E of Si with it, and this is an additive homomorphic encryption that M holds. G knows how to pick the right encryptions, multiply them, and he gets the encryption of the sum. He doesn't want to reveal to M, so it blinds it with E of R of the right of its choice of the right size to blind all the other elements, the sum, sends it to the other, multiply E of R into the blinded sum, to blind the sum, send it to M. M has the decryption key, and it sends back S, which is the sum of the blinding factor and the actual elements associated with matching elements, which elements in the set. And this paradigm of tagging those elements in the matching enables us to calculate the right sum. Of course, G, who contributed R, knows how to subtract R and gets the actual sum. So this was the solution, and there are a few nice things about this solution. The work explains the business context for it, and how you can have business problems that look simple, nobody knows how to solve it, and they require interesting cryptographic innovation, and what properties are easier to push when proposing a solution in a business context, why did it take so long, and what was needed. It's part of the paper. We put it in order to spill a little of the beans out, not all of them, but whatever we could. And why in around 8 years ago, well, I decided that crypto that computes, namely secure computing, rather than just communication secrecy, is the time to put it in business. And certainly this event is organized by Aarhus, which is a pioneering, one of the pioneering places for bringing practicality into secure computing. So the status of this work is that there are variants of it, it's implemented, and it runs routinely, I can say every day, and it shows the usefulness of the crypto R&D group. And it has now extended uses, some of which Payman talked about last week, because some of the cryptography was also open sourced, and other companies can use it, and we are happy that privacy overall is augmented with this contribution. And indeed, a lot of basic cryptography is available open source, but the specific, more what other people call fancy crypto and what we call crypto, and not even advanced crypto, is not yet there, and it's good to advance the state of the art. I know there are now libraries that do fully homomorphic encryptions and things like this, but sometimes even very simple elements that appear in many cryptographic papers for years, they are not available in the open, and then when you need to design something fast and demonstrate that it's useful, because not always in business you get an open, wide window of opportunity. The window is actually very short, and there are many opponents. Of course, there are many proponents, many opponents, and you need to perform and get things right, and you have to invest time and energy in it. So that's the state of this. Technically, if you look at it, the work uses a Poly-Hellman 76, which is now called Diffie-Hellman style commutative encryption. The commutativity of this function was pointed out in a paper by Shamir in 1980, in which he uses it to demonstrate how you can do equality. Elliptic curve cryptography was not yet at the time, so it was done over just simple elementary number theoretic problems. For additive encryption, the open source include Payet, and we did also experiments with other additive homomorphic things. And of course, it has variant, and of course, now it is implemented over elliptic curves. There are various protocols with various flaws, but with O, not with A. because we have proofs of security, and in the 80s you didn't need to have proofs to publish papers, so we had to complement what Polig-Hellman needed to do in 76 and Shamir in 80. So we did all this, and that's it. So it's nice. So one other interpretation of this work is that the double exponentiation can be viewed as a distributed oblivious PRF. That the two-party computes under the message, which is first hashed. That's actually the way to look at it. And of course, the exponents are secret, so it's more like a PRF, actually PRP, and the distributed oblivious PRFs have been used before, so it is shown secure under H, the hash function being random oracle, and the DDH assumption in the group, and distributed oblivious PRFs actually have been used in this context by a number of other works. And shuffle, the distributed oblivious PRF, is when when one party shuffles randomly and it leads to the cardinality by shuffling, and so you can only tag the entries, so it doesn't really compute. It's a little bit an extended functionality in which it doesn't really tell you just the cardinality, but it also tags the elements that are in common without knowing which elements they are, but this enables us to extend it to the sum by picking the associated elements. Okay, so as I said, Shamir used it to show equality check, and equality is the poor man's private set intersection. And other nice properties of this: it's flexible, it's scalable. You can run it when the two sizes are long and are large, or when one side is small. Important for cloud. If you have a cloud, that these are parallelizable because it's a vector computation. You can do incrementality, and it has very, very nice flexibilities that you may need in business applications. So it's not that we design something to solve a problem, but we actually design essentially a library to adapt it per needs. And that's if you work for industry, you probably know this, that this flexibility and agility is actually needed, and this implementation has it. Okay, so this was all nice and good, and this can be run when the elements are honest but curious, and there are enough business partners and business contracts in which the assumption that elements taking part in the protocol are honest, but you have to do actual risk management and decide with which party you want to run it, under what legal conditions, and so on. And it's of course much better to have a malicious PSI with extension to cardinality sum, and essentially have a library of solution of possible adaptations that give different solutions under the assumptions that the parties do not trust each other. You still write a contract and so on, but your risk management analysis does not rely on the other party to do the right thing, but you force the other party to take part in a protocol in which you are assured of that even if the other party is malicious and doesn't want to follow the protocol, it has to. Okay, so we want to retain the efficiency, so which means we don't want to use generic methods. In some sense, all malicious for plausibility, for feasibility result, you always have the GMW result that any protocol with commitments and zero knowledge and so on can be made into to cope with malicious adversary. There were many solutions for one side being malicious, or one side computing the interaction and intersection, and the other side being malicious. But we wanted the two sides to compute the intersection. And if you follow these protocols that were designed for one side malicious, then one side compute the intersection, it has to bring it to the other side, and just bringing it to the other side and proving that it's the right set makes the protocol typically inefficient. So it has been essentially a challenge. And of course, we want the extension, and the question is how to implement it. So we want to extend it while retaining the nice properties that I mentioned before, efficiency and other properties. So we need components that compute together and allow participant easiest way to convince in zero knowledge the other party that the protocol is being followed. And we want the symmetry, as I said, and we want efficiency and retaining properties. So it's the strict requirement for composing special components that smoothly together achieve robustness and performance. So now we have as a blueprint, as a plan, the honest but curious, and it has very nice properties, which some of them I didn't speak about, but I mentioned just a few. And we want to retain it. So we know what we want. We now we have to put components together. So it's like it feels like you have to create a symphony. You know, all the notes are known, the goal is known, the instruments are known. There are plenty of cryptographic protocols. There are many zero knowledge procedures and so on. And you need to put it together and do the right orchestration and so on and so forth. And this is what, after it was done, this is the way I felt like, even though I don't know nothing, I don't know anything about composing music, but I know something about composing cryptographic protocol under strict requirement. That is hard, and when it's done right, then the task and the results are satisfying. So this is the idea, and this was the plan. So so what's the protocol for malicious party, and what was achieved? And this is next. So protocol designed for malicious. So we have two party. And now, instead of distributed Oblivious PRF, which has nice properties like parallelization, we want to do malicious distributed Oblivious PRF. So distributed Oblivious PRF implies PSI, just by the two parties applying their keys, like in the honest but curious. Then, if you add a shuffle on the separated elements, you can get cardinality, as was shown also by the protocol. And if you have associated elements that are encrypted correctly, you can do the PSI sum. And we will have to develop the malicious shuffle, the distributed OPRF, the composition, and improve the performance as much as possible, or so orchestration. And I will talk about mainly about these two elements, the two reductions to PSI and PSI cardinality. So we will have distributed Oblivious PRF and two parties. Now I call them S and R. And they want to compute together the function on the elements coming from either side, which were, remember, these two elements. They all have a key. The key is distributed, two-party distributed Oblivious PRF. And if they have it, they can compute the they apply the distributed part computation on the two elements. And now, without shuffling, without anything, they both can see the matching and know the intersection. And if it's shuffled, if they apply the function to the two sets and they shuffle the sets, they permute it. And this is Macy's permuted and Google's permuted. Now they can just count matching and we get the cardinality. And of course, if there is associated sum, we can get the sum. So the rest of the talk, I hope to cover in a very general, in very general terms, the malicious shuffle distributed Oblivious PRF, SDORF, and the optimizations that were done in order to squeeze out more performance out of this protocol. And the first thing to look is the distributed Oblivious PRF that was used in the malicious thing. In the that we can use in the malicious thing, it cannot be the one that we used for the honest but curious. Why? Because we have a random oracle hash h of m to raise to the k in the right group. So raising to the k in the right group is fine. But the fact that you do a random oracle hash and you want to prove that you raise it to the right exponent, it's not friendly with efficient zero knowledge proofs. We want something much more algebraic. So we see immediately how the components for the honest but curious fail on the start. So we have to work hard and to find the right component. And we're working hard for so you don't have, so that the protocol can be run smoothly. And the principle is the design carefully, get efficiency overall. So we have to change the distributed Oblivious PRF, and there is one that first appeared by Bonnet and Boyen, which is f of k of an argument x is g to the 1 over k plus x, and this is one to use, and this is proven in the inverse Diffie-Hellman assumption, and it was used by Dodis and Yampolsky to do a sorry, to have a threshold PRF, and we had to modify it a little bit for the security proof, but it's beyond the scope. You can see it in the paper. So the input is X, there is a key, and this is computed. And if we want it to be a distributed PRF, then we have to just split the key, and then it becomes G to the 1 over the first key plus the second key plus the argument. And this is the distributed Oblivious PRF that we are going to use. But you know, it involves some computation. It's algebraic, nice, but it involves some computation, and you have to support it. You have to compute this. And so in particular, the parties have to come with and commit to their keys, K1 and K2. And then they have to perform the evaluation of the function. So let's say it's computing elements of R here on the right side. So it starts by having an homomorphic encryption and S encrypting with this homomorphic encryption the key K1, the key of the Oblivious PRF, and then the idea is that R will add its key and its input element to the homomorphic computation, and this, because the other side S owns the secret key, they can interpret this value, invert it, and raise G to this value. So of course, doing it directly reveals too much to S, so we have to do something. And the idea is to employ homomorphic, to not send directly what I showed before, just K1 plus K2 plus X, but to homomorphically blind it under the encryption, taking K1 plus, so it was encryption of K1, so adding K2 plus X to it, multiplying to it random factor R1, and adding the group order times R2, and sending a second element, which is G to the R1. And note here that if S now decrypts and inverts the element in the second flow under the homomorphic encryption, it gets, after it inverted, it gets 1 over K1 plus K2 plus X to the R1 plus Q to the R2, which is the blinded element, so it doesn't learn X and K2. And then when it takes G to the R1, the second element on the second flow in the right group, the Q to the Q times R2 cancel because it's the order of the group and it equals 1. And under the encryption in the under the raising to the exponent exponentiation, you actually get G to the K1 plus K2 plus X, because G to the R1 cancel the other blinding factor R1. The order cancels R2, the blinding factor cancels R1, and we get the evaluation of the result. So here is the idea how to use this.
Moti? Moti?
Yes.
Why do you add Q times R2? Because surely S decrypts and could just take it mod Q anyway, because she knows Q. So surely Q plus R2 doesn't give any security for R.
It's not true. It's not true. It helps because these are different groups. So when the decryption takes place, this is done modulo, and the homomorphic encryption is Kameny-Shoup encryption.
Yeah.
And then the G is completely another. I'm missing a few steps here. But
okay, no problem.
This is yeah. You will see there are things that you know at the first pass I cannot give you all details, but look at the e-print paper. It has all the algebra right.
Okay, no problem.
So it has also size constraints, like it has to be a larger envelope in which the actual thing does not live. It has to be, the decryption gives you an integer. It's larger than the inverted exponent itself, and this is how R2 comes into being. So it's as I said, it's a very sensitive thing, and you have to do the right elements. And of course, you have to do a malicious one, so it has to be accompanied by zero-knowledge proofs. So you have a commitment to K1, you prove in zero knowledge that you send an encryption of K1 under this, under your own homomorphic encryption. And every action has its own zero knowledge proof. And this is how we get it to be malicious. There are various details that you have to read about, but I gave you hints. Okay, and then this gives you the we do the same thing. So this is the major building blocks. We do it for the element X of K2. We don't do it just for one element. It's a vector computation. We do it for the elements Y of S in the other direction with another Kamenisch-Schupp homomorphic encryption. And this computes eventually the distributed Oblivious PRF on both sets, and then you can find the intersection. And what if you need to do only cardinality? Then you need to shuffle the distributed OPRF. I said we want to keep the basic plan, the basic blueprint from the honest but curious. So you have to essentially add so I pushed here 2 slides, one explaining the Kamenisch-Schupp encryption, which I already explained that it's not over the same group. It has size constraints and different algebraic domains, and you have to be careful. It's not something that you can gloss over the math and just do crypto by symbol manipulation. And you have to transfer it from that domain to the El-Gamal encryption, over groups where the inverse Diffie-Hellman holds. And then you add here a zero knowledge proof of shuffling and kind of commitment between this final element and this encryption and commitment to G to the R. It's another zero knowledge proof. Shuffling proofs are known. Growth works a lot on this domain to do it efficiently, and we can pick an efficient component. So we have zero knowledge argument for shuffling. We use the Bayer growth, which is essentially you have homomorphic encryption that you can multiply 2 encryptions and get the encryption of the multiplication. And it essentially uses take encryption of 1 and randomizes each ciphertext, and then you have to prove permutation. And this Bayer growth is essentially the state of the art. Zero knowledge argument for shuffling. So the protocol stages, just to recap a little bit, and I didn't tell all the things. You need, of course, to initialize a malicious protocol, one-time initialization. So the parties have to agree on a group, on the structure of the distributed Oblivious PRF, for which they can choose different keys in different runs or different set of runs. And each come up with Kamenisch-Schupp encryption and an associated Pedersen commitment and El-Gamal encryption. Everything is accompanied with correct proof, and they also do 2 out of 2 threshold homomorphic encryption to encrypt the associated values for intersection for set intersection cardinality sum that I didn't cover. Of course, per run, the shuffle DPRF with integrity assurance has to be run on both sets. and only then they can pick the right elements encrypted under the 2 out of 2 threshold homomorphic to calculate the sum, and then they each of them has half encrypted, provably half encrypted result. They send it to the other side with the proof, and then the other side can complete with its own key, its own half of the key, the different halves, each of them with a different half, and they get the same sum. So, so of course, all stages have zero knowledge argument of knowledge associated with them. For the implementation, it was done for efficiency under the Fiat Shamir, and we have the shuffle proof. We have range proofs because the ranges of the choice of the parameters are important for the blinding and so on. And at some point, we move an encryption from the Kamenish Shuk to El Gamal, and they all need proof of knowledge, and these are very interesting in themselves, but they are specializations of known techniques. And this is the way we achieve the first version of the symphony with all these components. And next, we need to optimize for performance, and we get into optimization techniques which are batching to gain performance. And this also gives us parameters for different size of batching, in which we can optimize the protocol whether we want to reduce communication and computation, and there is a trade-off in how much batching you do. But I will just describe you the batching techniques, which are interesting variants to gain optimization in our context. Our context is a vector computing, so you have a lot of things that go on in parallel, and you can batch them and minimize communication, or you can run them in small batches and reduce the computation per each element. So you can play with this, and this is a nice performance study that you need to do. But here are the techniques. So for example, you can batch commitments by vector commitments. So you have like Pedersen, which is G to the M, H to the R for random R. But if you have different generators, you can pack into the same value many messages, M1, M2, and so on. And you can just compute G1 to the M1 times G2 to the M2, etc., and blind it with H to the R. You can batch the Kamenish Shuk encryption by reusing the first element on many. So you know it's like it's a combination of El Gamal and Payet, very clever encryption method. So you can take the first element and G to the R and use it in many messages. We also the work also gave another batching technique, which is based on the Jurek Damgard extension of Payet. We extend the Kamenish Shuk in a similar way by instead of working modulo n square, working modulo ns and packing more messages inside. So it is possible, because I told you that the Kamenish Shuk is a Payet El Gamal, very nice extension. And we also batch Sigma protocols in this work, and And if you see a Sigma protocol for proving knowledge of so this is essentially a Schnorr protocol. When you prove you have G to the R and you know R and you want to show that you know X, and then you run Sigma protocol Schnorr style, and you show that this demonstrates X. So batching you can do again with you have, instead of G to the X, you have G to the X1 up to G to the Xn as input. You have G to the R that you know the discrete log of, and then you are challenged n times, but you can send back a compressed representation, which you verify this way, knowing the CIs and the relations that is supposed, and we have a proof that this show you in the same way that Schnorr shows you for one, this show you all together for all these elements. So I'm essentially on time, I see, at least. So all these exercises, and I didn't cover in depth all this work. The paper, as I said, as I showed at the beginning, is available on ePrint, and it's been a number of years, a number of summer internships in our group. First, Seth Karn, who is now a member of the group, was an intern who worked on it for a number of years. And then when he joined the group, Beihan Miao, who is currently with Visa, was a summer student, and she worked hard to put everything together. And I wanted just to mention and give them the credit for hard summers. And you will see the details if you look at the paper. And it's nice. Summer internship also forced the intern to put a lot of effort, and this requires a lot of effort in a short time. And this is the power of summer internship. So performance, what did we achieve? So malicious versus honest but curious. The version that minimizes communication does 6 times more. This is 6 times more work, more communication, compared to the honest but curious blueprint for the malicious. And when minimizing computation, we get 25 times more than the malicious computation that I showed you at the beginning. And this is a relatively this shows you the gain, because if we just took the honest but curious and had to prove that SHA-256 was applied correctly in zero knowledge to an element and raised to a power, this would be already much more than this. And this this shows you that all these great efforts and great combination and getting this symphony done was worth it. So this is the extra payment, multiplicative extra payment of the malicious versus the honest. Now there are not many protocols for symmetric malicious, and the one to compare against is the sort compare shuffle paradigm of Wang, Evans, and Katz from 2012. And our cost is 64 times now better. Here, this 6 and 25 is how much we had to pay compared to the honest, and this is how much we gain compared to the other malicious contender in the marketplace. And this is 64 times better for a 1,000,000 entry case. So this was implemented and checked against the other implementations. It works. So the summary, we know that malicious models are more costly. It's a very popular subject now. We heard a few talks about it in this meeting. With hard work, one can attempt to narrow the gap. So this is the working hard so you will not have to. So we work hard on the design so that the actual implementation will not have to work hard. It requires not just adding integrity, but revising tools, adding sensitive component driven by the need of integrity via zero knowledge. So we know that we have to cope with malicious. We have a generic tool family, which is zero knowledge proofs, and we work to integrate them the right tools. And this means that also the protocol has to change and integrate the right tools that work together with the integrity zero knowledge tool. So it gives rise to the integrity by design principle. So you design component and compose component that are easy to demonstrate in zero knowledge the validity of actions. And I think this is a very important paradigm for the very popular subject of malicious security. Another thing to note is that practical problems often lead to interesting questions which demand broad knowledge of the field. We have to know various encryptions, zero knowledge, and batching, and proof of all kinds of zero knowledge proofs, and we had to do it to put them together. And putting things together always leads to problems. For example, the Doddy-Siampolsky PRF is good for polynomial size domain, and we had to extend it and change the proof in some sense to exponential domain, because we cannot force the user to have sets of small size in our case. So there is a need to adapt. And the interplay of theory and practice is important, especially as cryptography becomes useful to system in our days. And this is why we started all this, and we started the group in Google, because the requirements of e-commerce on the web, which is cooperations between different companies, definitely now the cloud computing, privacy requirements, which are very important, security requirements, and many, many others, that now the internet is just gaining momentum. I believe it has many other applications and requirements for advanced cryptography. Now with Internet of Things, it's another things, and mobile systems, and we see them, and we need them, and we need cryptography in actual systems. So thank you very much.
Virtual round of applause. We've got time for people on mute for video to show their round of applause. Thank you very much, Moti. We've got time for a couple of questions. So if someone
I would have one.
Okay, whilst Carsten asks his, type yours quickly into the Q&A. Otherwise, so Carsten, go.
Yeah, Moti, I wanted to know, so you compare with this HKE that does everything in MPC and garbled circuits, but there's this recent work in the past few years, like this line of works of PSI where the output is secret shared, and you then can do a secure computation on the outputs. I remember there's this work by Chiampi and Orlandi, and I think there's also some work by Benny and maybe some other people where they do this. So maybe these protocols could either be compared to or could be tweaked in a way such that they could be comparable to what you are doing. Or are you considering this, and maybe they're only semi-honest or so?
No, you're right. We we have to compare them, but I think they are one-sided malicious. That is there, and I mean we probably should compare. We compare to some other thing, and sure, and I'm sure we'll continue to compare. We compare to
as I said, it might be.
Rindal and Rosulek, malicious secure private set intersection via dual execution. That was 2017. The very recent one, I don't think we compared, just because we essentially we did the work before, but it, I mean, or concurrently. But you know, there are new interns coming every summer, and we are going to continue to prove it. And in the process of improving, we are going to compare. And it's a fair. It's a fair question.
All fair. They might also.
Carsten.
I'm
one
out.
more question.
Okay.
You've already had two. You can have more. Right, I'm going to be very strict with you. Right, we've got time for one very quick question, which is a really interesting question from Thomas, who asks, are you planning to deploy this in Google, or has it already been deployed?
Has this been deployed?
Yeah, or is it being deployed? Is it going to be deployed?
I don't. I represent myself in this talk to the largest extent.
Okay.
It's a tool that is available, programmed and implemented, and it works on Google infrastructure. And when Google decide to say more, they will.
Okay, so Google hasn't decided to say more. That's fine. Sorry for the others who want to ask questions. We've got to move on. Thank you very much, Moti. That was a really, really cool talk. Thank you.
Thank you.
And the